Welcome back to another video. We now had two videos on martingale convergence, and today there's a third one. Today we are not dealing with almost true or L1 convergence, but with weak convergence of martingales. And that's a bit different because we'll have a sequence of martingales which converge in some sense. And actually that's what you already know because that's the central limit theorem. But as we had the central limit theorem in the last semester, it was a main point that the random variables which we were averaging over were independent. And now they have to be a martingale sequence. So they have to be the difference of the martingale at 2 time points. And that still works, and we will see how that works now. So, the central limit theorem for martingales. And let me just dive in and tell you what this theorem is. As I told you in the initial sequence, Mn, so we have a sequence of martingales. And x is the difference of the martingale at 2 time points. And the martingale with index with n runs until time tn. Yes. So we have the following. X is this martingale difference. The maximum of the x goes to 0 in L1 or so. And the square of this difference, summing up to tn and tn, so n goes to infinity, converges weakly to some sigma square. Then the martingale at the end time point converges to a normal distribution. So it's a central limit theorem because we have convergence to a normal distribution. And the regular central limit theorem for independent random variables is also covered here, as I will show you in this example. So let's just assume for simplicity the x's have expectation 0 and variance sigma square. And we are using this martingale. So the nth martingale is this here. And maybe we should also say that Tn here and Tn equals n. And then, as we know, we not average over this, but we take the sum of the xt's and divide by 1 square root of n. That converges to a normal distribution. That's what we know. And why is that? When we just want to apply the above theorem, so that's mtn. So what's the martingale difference? They all have the same distribution. First, the following. So this here is the expectation of x1. As you might, no, that's not the, that's the variance. So that's the variance actually, or that's the variance of x1. That's finite. And we also need here something. We need this here. This here must converge to 0. So that means the probability that x1 is bigger than t drops faster than 1 over t squared. And if we have this, we can apply the martingale central limit theorem. So we would have to show the two things here. Well, the second thing, that's okay anyway, because that's the law of large numbers. Because the difference squared, that's xt divided by n. I'm summing over all these from 1 to n, so that so xt squared divided by n, that converges to the variance of x1, which is sigma squared. So that's okay anyway. And for the first things, so the maximum has to go down to 0 in L1. So what's the expectation of the maximum of xs divided by square root of n? Well, I can also say it's an integral over the random variable bigger than t. And I can also do the square root of n to the other side. So I get this here. And what does this mean? That means when it's the maximum bigger than t, It's bigger than t if there is at least 1 which is bigger than t, which is 1 minus nothing is, so 1 minus no random variable from x1 to xt exceeds t times square root of n. And the probability that none exceeds it. Okay, power of n because I have n random variables, so I need here the probability that 1 exceeds it. Or 1 does not exceed it, and that's 1 minus it exceeds t square root of n, so like this here. I'm using here t square n and divide by t square n because I have here that here t squared, here t, so here's the square of this thing here. That goes to 0, so the numerator goes to 0. And this thing here is t square n. So this is essentially, if that here would be very small, 1 minus something very small divided by t square n to the power of n. That converges to 1, because that's connected to the exponential limit. That would converge to 1. Pointwise, and 1 minus 1, okay, that's 0. Integrating over 0 gives 0. So that's this here. And let us see how we can prove this central limit theorem for martingales. And we need one lemma, which is central, which is the following. We have random variables u and t. Un converges to u in probability. Tn and un have to be uniformly integrable. And Tn converges to 1 in expectation. Then, okay, un converges to u and Tn to 1. Then the expectation of Tn un, okay, un is close to u anyway, and expectation of Tn converges to 1, so the expectation of Tn un converges to u then. How can we show this? We are showing that Tn times un minus u converges as n goes to infinity to 0 in probability. Because then we know that Tn un is uniformly integrable, and Tn times u is also uniformly integrable by assumption 2. Then the convergence here also holds in L1. And that means the expectation converge. And the expectation, well, Tn un converges to u, so that's then, when we have this, we have L1 converges, so expectation of Tn un converges to the expectation of a limit of Tn times u. Expectation of Tn is 1, so that's it then. So how do we prove this? For epsilon bigger than 0, I take a k such that the probability, that the supremum over all n probability of Tn bigger than k is less than or equal to epsilon. Why can I do this? I can do this because the Tn's here are uniformly integrable. Well, then they are also tight in here. That's basically tightness of the family Tn. There is something which you will believe me. If x times y is bigger than delta times epsilon, then either x is bigger than delta or y is bigger than epsilon. Okay, if everything is positive, of course. Because otherwise, x times y would be smaller than delta times epsilon, which is forbidden. Okay. And then I can study the lim sup. N goes to infinity of the probability that Tn times un minus u is bigger than epsilon. Well, I can write epsilon as epsilon divided by k times k, okay. And then as we have here, if this here is bigger than this, then either, okay, yeah, let me do it differently. Let's here, k times epsilon divided by k, then either Tn is bigger than k or u minus u is bigger than epsilon minus divided by k. So this probability I can bound from above by, okay, either Tn is bigger than k or un minus u is bigger than epsilon divided by k. The latter here converges to 0 because un converges to u, and the other is less than epsilon. Which means we have shown convergence in probability. Okay. Well, we need one more thing, which is an estimate for the exponential function, which is not too hard. Because I will use Levy's theorem for proving the martingale central limit theorem, which means I have to show convergence of characteristic functions. So this here holds, and yeah, well, this here also holds. Let me start with this. So that's easy. You probably know this from no, maybe you do not know this. So yeah, taking the square here solves everything. So taking the square here, here I have 1 plus x squared, and here I have e to the power of x squared, and that's just a thing that you learned in the first semester then. The other thing we can quickly compute, e to the power ex minus 1 plus ix times e to the minus x squared over 2. Let me see what the error is. And the error is here, well, it's a factor of e to the rx it should be. And rx should be small in this sense here. So yeah, well, all the things here are O of 1, and I get an additional factor of 1 plus order of x to the 3, which means I have to prove that this difference here is of the order x to the power of 3. Yeah, when I compute this here, well, e to the power ix, that's 1 plus ix, well, minus x squared over 2 plus something of the order x cubed minus 1 plus ix times 1 minus x squared over 2. The next term will be x to the power of 4 over 4, but that's, I can hide here in the O of x cubed, so like this here. And when I compute this, well, so this one here goes against this product. I have the plus ix here times this one comes with a minus, which goes away with this here. So this goes against this here. I have a minus x squared over 2 times this one times this minus a plus x squared over 2. So this here also goes away. I would still have the ix times x squared over 2, but that's of order x cubed. So I have shown that that's here is of order x cubed. OK. And then we come to the proof of the martingale central limit theorem. First of all, well, I will assume that this here holds. Otherwise, I have to restrict something. That works very similarly. That's written in the manuscript. And we are going to show this here. So e to the power, expectation of e to the power I lambda mu t n n. So that mu t n n converges, as the theorem said, to x, which is normally distributed. So this here should converge to this exponential, and then we are done. And I'm writing that a bit funny, e to the power I lambda mtnn. Well, we had here e to the ix. I can write like this here with this function r. I did that here. So I have this here, and I have this here, and I completely forgot an expectation, didn't I? Maybe I really completely forgot an expectation around all this. Yeah, so that must be an expectation in front of everything here. And that's of course 1442. So what do I need? We use the last lemma. That lemma we use. So we need un goes to u, tn and t and un are uniformly integrable. And expectation of tn goes to 1. So un converges to u. That's clear, I say here. So r is small anyway. And this here is assumed to converge to sigma square. In probability, and therefore that also holds here. Then tn and un should be uniformly integrable. For t and un, that's not a problem because tn times un is this here, and that's bounded by 1 in absolute values. And for the tn, so that's this thing here. Well, I can write it like this by pulling out here the last term. Then we had that 1 plus I times something is less or equal than this here. Times, yeah, I just write that down. That is essentially, well, maybe there is a constant which I would need. Goes to lambda square sigma square. And the other thing, I estimate by 1 plus lambda times the maximum. But by assumption, the maximum here converges to 0 in L1. So that also converges to 0. Tn is also uniformly integrable. And for the third property, I need that the expectation of Tn converges to 1 here. But the expectation of Tn, yeah, let's see. So expectation is the expectation of the conditional expectation. I'm conditioning on ftn minus 1. I can pull everything out except for the last one here. I have a 1 from here in the expectation, and I have the xtn from here. But the expectation of xtn given ftn minus 1 is 0 because I have a martingale. I never used that I have a martingale up to now, but now I use it like this. So here I have 1, and it can continue this until the start, and I get a 1 here. And I'm done because then I can really apply lemma 14.143 for the proof. So here is an application which we could not deal with before. M, that's something we know. The y's have expectation 0 and variance 1. So this here converges. Okay, that here converges with t equals n, and for n goes to infinity, to a normal distribution. But we are not having this. Here we're having a stochastic integral. We're integrating m. The integrand is h, and h is this thing here. And by the law of large numbers, if s is large, that converges to 1, but it is not 1. So if I would integrate 1 against m, well, that would be fine because that would be m, but I'm having it a bit differently, and that violates the usual independence assumption, but it does not violate that h times m is a martingale. Because we know if m is a martingale, h times m is also a martingale. So I can write that down. Okay, what do I have to do? I have to write h, which is written here, times mn. So the difference in the m's, that's 1 over square root of n, times 1 of the y's, so like this here. And in this double sum now, there are not so many independent things. So that's not a sum of independent random numbers. But it's a martingale. And we have to check the assumptions in order to apply the martingale simple limit theorem. So what's the expectation of the maximum? Well, the y's are bounded. The y's are bounded. And therefore here I have a bounded thing, and I can show, and I have that the expectation of the maximum goes to 0. And the x squares, well, now there is something nice. So the x squares, y is squared divided by n, and then this thing here square. That converges to 1, I claim, because, well, if s is large, this here converges to 1. And ys square average of this also converges to 1. Yeah, that means I have converges to 1, and I can use the martingale simple limit theorem in order to show convergence to the normal distribution. Okay, that was it, and next time we will be dealing with martingales in continuous time. See you then.